So I think you guys got the first step right and maybe had a little trouble with, this step. You got this step right and the next step maybe you had a little trouble. So what's this going to turn into over here? Am I drawing this right? Yeah. So this started neutral and it's gaining electrons. It's at the final head. So this started positive and it's gaining electrons, so it ends up neutral. This carbon lost the electron, so it ends up positive. Of course, I could have put the positive charge here and the bromine here. Now we have to take the hydrogen. Now, where is the bromine? The bromine is going to take the hydrogen. And where's it going to get the electrons from this bond? So that's the one detail you might not have gotten in your mechanism. Even though the negative charge is on the iron, it's actually the bromine that's donating the electrons here. So this is a technical step that people might get wrong. And that takes us back to here. Remember that we said this was a Lewis acid catalyst, so it has to be regenerated in the last step. It's been regenerated. So there are some little technical details that's hard for people to remember how to get the arrows right here, but for the most part you guys knew how to do that. So we've seen how the Lewis acid here puts a positive charge on the bromines, making them more electrophilic. Notice that even though the positive charge is on this bromine, this is the bromine that acts like the electrophile. That would be another step that would be easy to forget. We've sometimes seen in the past, if you have a positive charge but you have a complete octet, it's actually the thing that you're attached to. That's the electrophile. And this positive charge is just making this bromine into a good leaving group. In the past, we've seen that if you have a positive charge and a complete octet, that makes the thing that you're attached to into a good electrophile, and it makes you into a good leaving group. So this was the electrophile here. So there are some little details that are difficult, and you definitely could be tested on this mechanism. That gives us this product. Because the mechanism is a little tricky though, I wouldn't normally draw the mechanism unless I was asked for it. It's much simpler just to go from here to here. So the most important thing that we have to do here is memorize what is the electrophile that will end up attached. Well, when you see these reagents, you should know what's the electrophile that will end up attached? A bromine. That's the most important thing. Although you need to be able to draw the mechanism if you're asked for it. So here's our product. Incidentally, here's ethylene. This is a reaction we saw last term. Let's just describe in words what would happen here.
First you get oxycyclobromide, and then the other bromine attaches
you would get
the carbon.
One up and the other down.
Yeah.
Answer to each other.
We would call this a cyclic bromonium ion. Cyclic bromonium. And then we would end up with both bromines attached. So notice that normally, what happens when you treat a carbon-carbon double bond with a halogen? You normally destroy the double bond, and you end up with two halogens. That's totally different from what happened here. This was an electrophilic addition, right? This was an addition, whereas this overall was an electrophilic substitution. Why do we do a substitution here and an addition here? Well, we already described why. If we did this type of reaction, this addition up here, we wouldn't be able to reform the aromaticity. So this just reinforces how important it is to reform the aromaticity. We don't get the normal double bond reaction because that wouldn't reform the aromaticity. Instead, we get a substitution reaction. This is actually pretty similar to what we saw with when we were having nucleophilic attacks on carboxylic acids and acid derivatives, because remember the way we reformed the carbonyl was addition and then elimination. That's exactly what we're doing here. Addition and then elimination to reform this double bond. In the carbonyl, we needed to reform the carbonyl double bond, and in benzene, we need to reform the benzene double bond after it's been unformed. Incidentally, just to remind you, another way that benzene is often drawn is like this. So you might see it drawn with a circle. And also just to remind you, it doesn't matter where you put the double bonds, because these are equivalent resonance structures to each other. So any of these would be an acceptable product in this case. You can see it drawn any of these ways. This reaction is generally done with bromine or chlorine, not usually done with fluorine or iodine, usually with bromine or chlorine. So that would be a halogenation of benzene. Now, let's draw what the product would be here. Now, again, the mechanism is kind of tricky. I don't know if we want to spend the time to go through the whole mechanism, but let's start by just making sure we know the product. So let's skip the mechanism and just draw the product. Now, the most important thing to see here is that neither of these is the exact electrophile that will end up attached. We should basically just memorize that this is the electrophile that ends up attached. I think one of you had one too many oxygens here, so there should be 2 oxygens, not 1 oxygen. For the most part, you should just memorize that. Notice it's not obvious from looking at these reagents what the electrophile is going to be, so you should just memorize what it will be. Do you know what the name is for this substituent?
Nitro.
Nitro. That's a very important name to know. Nitro. This is a nitro substituent. It's also important to know what the Lewis structure is for a nitro group. You could go back to general chemistry principles and figure that out by counting the valence electrons, but we'll just memorize it. This is the Lewis structure. You should be able to figure this out using your general chemistry skills, but it's better just to have it memorized. Notice that there's some very interesting things about this. First of all, of course, there's another resonance structure where the negative charge is on this oxygen, and the pi bond is over here. One thing that's interesting is even though the nitro group is neutral, it does have charges. There's no way to get rid of the charges, even though overall it's neutral. Does this nitrogen have a lone pair?
No.
That's a very important fact about this nitro group. This nitrogen does not have a lone pair. Most nitrogens do have lone pairs, but this nitrogen has 4 bonds. Would we think of this nitrogen as electron donating or electron withdrawing? Because of this positive charge. Most nitrogens are electron donating because of their lone pair. Most nitrogens can donate their lone pair, but this doesn't have a lone pair. That's the most important reason that you need to know this Lewis structure here. If you just looked at this NO2 group over here, you might think that the nitrogen was electron donating because you might think it has a lone pair, but it doesn't. So we should know that this is the Lewis structure for nitrogen. All right, now again, you might be, unless you're asked for it, I wouldn't draw the mechanism. I would just go straight from the starting material to the product here. You might be asked for the mechanism, and again, there's a couple tricks there. If you want to, we can go through it, or if you want to, not.
I think we know.
We know this.
Yeah.
Okay. So the sulfuric acid here is just a catalyst.
Yeah.
Basically, what the sulfuric acid is going to do is make this into a better electrophile. We know acids make things into better electrophiles. But again, because the mechanism is a little complicated, I wouldn't normally draw it unless the question asked for that.
And this is called?
Nitration. That's a good point. This was halogenation of benzene. It's good to know these names. I think this is a pretty intuitive name. This is nitric acid over here. This is nitric acid and this is sulfuric acid. This is nitration.